Fly-by-Night Airlines is updating its security system at a major airport. The budget for new metal detectors is $75,000. The airline has a maximum of 18 security guards available for each shift. There are two types of metal detectors available. Unit A costs $5,000, requires one security guard, and can process 120 people per hour. Unit B costs $7,500, requires two security guards, and can process 300 people per hour. Since Unit B has a better reliability record, the purchasing agent has mandated that at least 4 of the units must be Type B. Determine the number of each of the type that should be purchased in order to maximize the number of people that can be processed.
First, we have to define our variables. The X variable is the quantity of scanner A, and the Y variable is the quantity of scanner B. We know this because it is asking for the number of each type that should be bought. Our constraints are X is greater than 0 because you can't buy a negative amount of scanners, and Y is greater than 4 because 4 scanners have to be Type B. 5,000X plus 7,500Y is less than or equal to 75,000, represents the total budget. Each scanner A costs $5,000 and each B costs $7,500. The sum of this cannot be more than $75,000. When converted to this slope-intercept form, so we can graph it later on, X plus 2Y is less than or equal to 18, represents the number of security guards. Only 1 is needed at scanner A, but 2 are needed at B. The total amount of security guards per shift cannot be more than 18 guards. Again, we converted this to slope-intercept form to make it an easier to graph.
Now that we know our constraints and variables, we can start graphing. Because our equations have small y-intercepts, we went up by 1 for our x and y axes. First, we graphed x, and is at least 0, and y is at least 4, because they are simple to graph. For the other two, we started with the y-intercept, then used their slopes to draw the line. Remember that these are all solid lines because we are only using less than or equal to or greater than or equal to signs. Using arrows to mark which way to shade each line and finding feasible regions where all inequalities work. In this case, it's a quadrilateral. Finally, we can see our corner points are of the feasible region 9, 4, 0, 4, 6, 6, and 0, 9.
After finding the feasible region, we can now use the corner point in the objective function. This equation, 120x plus 300y equals f of xy, is what we use to find the maximum amount of people scanned. 120x stands for the amount of people scanned per unit A, and 300y is the amount of people scanned per unit B. This means that f of xy is the total amount of people scanned. Using our corner points from the feasible region, we then substitute each coordinate into the objective function to determine which is our optimum solution. 9, 4 then has an f value of 2,280, 6, 6 has an f value of 2,520, 0, 9 has an F value of 2,700. And finally, 0, 4 has an F value of 1,200. Now we know 0, 9, which is 0 scanner A's and 9 scanner B's, is our optimum solution, with 2,700 people scanned per hour.
Now that we have the answer, we can find an alternate solution. This is when we change the coefficients in the objective function to get another corner point as the maximum people scanned. There are lots of different alternate solutions. This is just one example. Here we change the objective function to 200x plus 275y equals f of xy. We use the same process as the original solution to find the alternate corner point. For each coordinate above, substitute x and y values into the objective function. Now the point 6, 6 has the highest amount of people scanned at 2,900 per hour. By changing the objective function, we just got an alternate solution of 6, 6. Thanks for watching, and we hope you now understand how to solve linear programming problems a bit better.